Uh, so take a basis of a finite dimensional vector space. Suppose I have a basis of finite dimensional vector space. That means a finite set. That is the definition of finite vector space. That there is a finite set which is linearly independent, whose linear span is the whole. Yeah, just like E1 and E2. If I take in R2, their linear span is the whole space, and E1 and E2 are linearly independent. Similarly, I showed you that the n basic column vectors E1, E2, En, they are linearly independent in Rn. So Rn is linear span of E1, E2, En. E1 up to En are linearly independent. So E1 up to En is a basis of the given vector space. So if I have a finite dimensional vector space and V1 up to Vn is a basis, then every vector can be uniquely expressed. This is important. Every vector is a unique linear combination of elements of the basis. These A1, A2, An, they are uniquely determined. So if I have a basis, that means it's a linearly independent set whose linear span is the whole space, then every vector in V is unique linear combination of V1 up to En. So look at this situation Rn. Rn is linear span of E1, the standard basic column vectors, and every vector V. Suppose V is the vector V1, V2 with components Vn. Then V is equal to V1, E1, V2, E2 plus Vn, En, and these Vi's are obviously uniquely determined. So every vector in Rn is a unique linear combination of E1, E2, En. But you see, I showed you R2 is linear combination of E1 and E1 plus E2 also. So every vector can be uniquely expressed as alpha 1 E1 plus alpha 2 E1 plus E2. You can easily check that this can be done. Okay. So whenever I have a basis, then every vector in that vector space is a unique linear combination. So there's a question: is a unique linear combination, or even you do not even? But you see, yeah. Okay. Yeah. Okay. So let us prove this. Let us prove this fact. We show that all bases of a finite dimensional vector space have same cardinality. Yeah? They contain the same number of elements. Okay. All bases of a finite dimensional vector space have same cardinality. They contain the same number of elements. So this proposition I am leaving you as an exercise. It's a easily proved fact that every vector can be uniquely expressed as a linear combination of basis vectors. Yeah. So let's now we want to prove that any two bases of a finite dimensional vector space have same number of elements, and that will lead to the definition of dimension of a vector space. Okay. So take a set V1, V2, Vk. Suppose it's a subset of a vector space. Then the linear span of S consists of infinitely many vectors. If I take a real vector space, it will consist of infinitely many vectors. Even linear span of one non-zero vector has infinitely many vectors. So if I take a non-zero vector, say in the plane, and take its linear span, it consists of all vectors sitting on that line which is containing the vector. So linear span of even a one non-zero vector has infinitely many vectors. So the linear span of these k non-zero vectors, yeah, this has infinitely many vectors. But in this linear span, if I take k plus 1 vectors, they will be always linearly dependent. Yeah. Okay. So my linear span is linear span of k vectors, and I'm saying that any k plus 1 vectors in this linear span will be linearly dependent. So if a vector space is linear span of k vectors, then its dimension cannot exceed k. That is a consequence of this fact. Yeah, because any k plus 1 elements will be linearly dependent. If the dimension exceeded k, then we will have more than k vectors which are linearly independent. But this lemma says that if I take a vector space with a linear span of k vectors, then any k plus 1 vectors in the linear span are linearly dependent. Okay, this is very crucial. This will immediately imply that any two bases of a finite dimensional vector space have same number of elements, and that number is called the dimension. Okay, so we are not appealing to any geometric intuition here. So our geometric intuition fails beyond dimension 3. We can't imagine 4-dimensional, 5-dimensional spaces. So we have to come out with a definition which can be, which is efficient, which is algebraic, and it can be tested. Okay, the criterion can be tested. We can find out the dimension simply by writing some programs. Okay, so this lemma will imply that dimension of vector space is a well-defined notion. Okay, so let's prove this, that any k plus 1 elements in linear span of k vectors are linearly dependent. Okay, so let us look at the set of k plus 1 vectors. We are saying any k plus 1 vectors. So I take k plus 1 vectors. Yeah, I take k plus 1 vectors in the linear span of S, and I want to show that these k plus 1 vectors are linearly dependent. That means I must produce a non-trivial linear combination. Yeah, I have to produce a non-trivial linear combination, alpha 1 u1 plus alpha k plus 1 uk plus 1 equal to 0. Somehow I have to produce a non-trivial linear combination of u1, u2, uk plus 1, which produces a zero vector, assuming that linear span of these k vectors is this space. Okay. Yeah. So let us write down. So each one of these vectors, what is the information we have? Each one of these vectors is a linear span of these k vectors. So write down this equation. Ui equal to summation aij vj, where j equal to 1 up to k. So this ui is in the linear span of v1 up to vk. Ui is a linear combination of v1 up to vk. I write the coefficients as aij. I do it for every r. Okay, there are k plus 1 vectors which are linear combination of these k vectors v1 up to vk. Yeah, so that means ui's can have these formulas. They are linear combination. Okay, now so this gives rise to a k plus 1 by k matrix, because I have k plus 1 vectors which are linear combination of k vectors. So in those relations, the coefficients aij, okay, coefficients aij, I is varying from 1 up to k plus 1, but j is varying from 1 up to k. So if I collect all those coefficients in those linear combinations, I get a k plus 1 by k matrix. Yeah. So this k plus 1 by k matrix, it has more rows than columns. Yeah. It's a tall matrix. There are more rows than the columns. Yeah, there are more rows than the columns. There are k plus 1 rows and there are k columns. K plus 1 by k matrix. Then this is my matrix A. Then I want to see that XA is 0. There is a non-trivial X. This is non-zero. Okay, let us see that. Why I can find, if I have a tall matrix, there is a non-trivial X. So instead, I look at A transpose. K plus 1 matrix. So there are k rows and k plus 1 columns at bottom of A Y. But this matrix A transpose has k rows and k plus 1 columns. So it's a fat matrix. It's a fat matrix. There are k rows, lot more columns. And I have this homogeneous system of linear equations. So when I convert this A transpose into its row echelon form of A transpose, it will have k rows and k plus 1 columns, and therefore at least one column vector, there will be one, when you look at the pivots, number of pivots cannot exceed k, because there are k. So there is at least one non-pivotal column. Now if you have a homogeneous system of booleans, which give rise to one non-pivotal column in the row echelon form, then the given homogeneous system of linear equation has a non-trivial solution. Yeah, this we have seen before. The number of free variables is equal to number of non-pivotal columns in the row echelon. But if I have k by k plus 1 matrix, then there will be at least one non-pivotal column, and therefore A transpose A transpose Y, that has a non-trivial solution. Once it has a non-trivial solution, then I can just look at A transpose and just look at A trans and A transpose, that is equal to 0. So this is my vector X. This is my vector X, or we can call it vector C, so that C equal to 0. So if A is a tall matrix, which means there are more rows than then there is a row vector C, so that C is 0. Okay, that's what I'm saying here. That this k plus 1 by k matrix, which came from the coefficients. When I write these k plus 1 vectors as linear combination of k vectors, then I get this k plus 1 by k matrix. So this discussion says that there is a vector C, row vector C, so that C equal to 0. That means if I display the components of 1 by k matrix, so this has k plus 1 components, C1, C2, Ck plus 1. Yeah, then I apply Ca is a row vector, and in the components of the row vector are these: Ci equal to 1 up to k plus 1 equal to 0. So this I get this linear relation among Aij for every j, and now go and look at, say, C is this vector, Ca equal to 0. I look at this linear combination Ci ui. Okay, but ui is this sigma Aij Vj, and now I can interchange these two sums and Ci Aij Vj. This relation among V1 and Vk. So that shows U2 Uk plus 1, this linear combination is 0. Not all the Ci's are 0, because Ci's are components of this non-zero vector. So therefore, these k plus 1 vectors are linearly dependent. On this is a very important fact, that linear k vectors, if we take or more in these, now this gives rise to the notion of dimension of a vector. Fundamental notion in this course. Two bases. Yeah? Any two bases of a finite dimensional vector space. Any two bases of a finite dimensional vector space, they have the same number of elements. Yeah? Any two bases of a finite dimensional vector space have same number of elements. So suppose that S and T are two bases. I want to show that they have same number of elements. So suppose that number of elements in S is less than number of elements in T. But linear span of S is V, linear span of T is V, because these are two bases of V. Linear of S is V span. T has more elements than number of elements in S. So by this previous lemma, elements of T are linearly dependent. But this is a contradiction, because S and T are two bases. So bases have two properties. Their linear span is the whole space, and the elements in a base. So if S and T have different number of elements, then the number of elements in T is more than number of elements in S. But linear span of S is V, and therefore elements in T are linearly dependent. But this is a contradiction to our assumption that number of elements in S is less than number of elements in T, and therefore any two bases have same number of elements. Any two bases of a finite dimensional vector space have same number of elements. Yeah. So this is associated to a so Rn is finite dimension. Yeah, because Rn was set less than n vectors. Because E1, E2, En are linearly independent and they are linear for R Rn and union volumes of vectors. Okay, so the number of elements in a basis of a finite dimensional vector space is called the dimension of that vector space. Okay, so every vector space is either finite dimensional or infinite dimensional. Okay, infinite dimensional vector space cannot have a finite basis, right? So, and a finite dimensional vector space has the property that any two bases will have same number of elements. Okay, any questions so far? Okay, so let's proceed. Okay, let me give some examples of bases. So I said E1 up to En. Okay, E1 up to En, they are bases of Rn. Okay, this E1 up to En, the standard column vectors, they constitute a basis of that. So Rn is one dimension. Rn is n dimensional. So R2 is two dimensional. R3 is three dimensional. R is one dimensional. R is one dimensional because any non-zero real number, uh, produces the set of real numbers. Okay, as scalar multiples of a fixed non-zero real number produces the entire real line. So R is one dimensional. R2 is linear span of E1, E2, that is two dimensional, and Rn is n dimensional. Yeah. Now let's see column vectors of n by n matrix. Take a n by n matrix which has coefficients from f. Yeah. Then they form a basis of Fn if and only if A is invertible. Yeah. So if I have n vectors in Rn, I'm interested in knowing when it is a basis. So what do I do? If I have n vectors in say V1, just a minute. I have vectors V1, V2, Vn in Rn, and I want to test whether these are linearly independent. So I make a matrix whose column vectors are V1, V2, Vn. Okay, column vectors are V1 up to Vn, and I want to test whether these are linearly independent or not. Okay, so linear independence means that if I take a linear combination, and suppose this is the zero vector, then all the xi's are zero. That is the meaning of linear independence. Okay, but this linear combination of these n column vectors, I can write, suppose this is my matrix A, that is same as A times x1, x2, xn equal to 0. There are two ways of looking at AX. AX equal to 0 means I take the first row vector of A, take the dot product with x, that gives second row vector, dot product with x is 0, etc. But AX can be also realized as linear combination of its column vectors. So AX equal to 0, have a non-trivial linear combination of V1, V2, Vn equal to 0 means that AX equal to 0, this system, homogeneous system of n linear equations in n unknowns, has a non-trivial solution. But we have seen that a matrix is invertible if and only if AX equal to 0 has only trivial solution. So that proves this statement that column vectors of a n by n matrix form a basis of Fn if and only if A is invertible. Yeah, okay. This is the proof. Look at PNR. Look at PNR. Okay. PNR is consisting of linear combination of 1T Tn. And 1T Tn, I have proved before, they are linearly independent polynomials. They are linearly independent monomials. And so PNR is a PNR is linear span of n+1 linearly independent polynomials. These are n+1 linear independent polynomials. Their linear span is whole of PNR, and therefore dimension of PNR is n+1. Remember, PNR consists of vector space of polynomials of degree at most n, and its dimension is n+1 because PNR is linear span, so its dimension is n+1. Okay. Now let's look at the space of look at all the real matrices of fixed size m by n. Okay. All the real matrices of fixed size m by n. Now, I want to produce a basis of this vector space. This is a vector space under addition of matrices and scalar multiplication of matrices. This is a vector space. I want to detect the dimension of this vector space. So, in order to detect the dimension of this vector space, I need to write this as linear span of a linearly independent set. So, I'm producing that linearly independent set. Look at the matrix Eij. This is m by n matrix, where 1 is in ijth position and 0 elsewhere. Okay. So suppose I'm looking at R2 cross 3, 2 by 3 space of 2 by 3 matrices. Okay. Space of 2 rows and 3 columns. So I have these 6 degrees of freedom. Really speaking, I have these 6 degrees of freedom, and it turns out that this is a 6-dimensional space because I look at matrices. If I take a arbitrary 2 by 3 matrix, okay, then it looks like A, B, C, D, E, F. But then I can write this as A times the following matrix 1, 0, 0, 0, 0, 0 plus B times 0, 1, 0, 0, 0, 0 plus C times 0, 0, 1, 0, 0, 0 plus D times 0, 0, 0, 1, 0, 0, etc. So this 2 by 3 matrix is a linear combination of these 6 matrices, where each matrix is obtained by having one as one entry and other entries are 0. So I can do the same thing for the space of m by n matrices, m by n real matrices. Eij denote the m by n matrix where 1 is in the ijth position and 0 elsewhere. So if I take arbitrary matrix Aij in F m cross n, then this matrix is a linear combination of these Eij's just like this. So Eij, the linear span of these mn matrices is the whole vector space. Yeah. So this says that f m by n is linear span of all the Eij's where I equal to 1 to up to m and j equal to 1 to up to n. Yeah. And you can check very easily that these Eij's, maybe I should have better notation. This should be small Eij. They are linearly independent. Because if I take linear combination of these Eij's, and these are the coefficients in the linear combination, yeah, there are mn matrices of the kind Eij, and if this linear combination produces this matrix A, and if it is 0 matrix, then every Eij must be 0. Yeah. So therefore, the space m by n is mn dimensional because these Eij matrices are mn in number and they are linearly independent. So the space of say 2 by 3 matrices is 6-dimensional. Yeah. Then what is the dimension of n by n matrices with complex entries? Same answer, n square. This is n square. There are n square entries in a n by n matrices, and we can freely choose them.